Chapter 6, Section 5, we're going to talk about exponential growth and decay. In a minute natural phenomenon, quantities are going to grow or decay at a rate proportional to the size, meaning that if we have some type of population, say y, that population is going to be some function of time, right? There's a certain population at a certain time. So it's a function of time. And then it's going to be proportional to the rate of growth. And the rate of growth is just how much the population is changing over how much time is changing. So that is a derivative. The amount of population, how the population changes at what the rate changes of. So I can write it like that, or I can write it dy over dt, how much the population changes over the time that changes. And these are proportional, meaning that I can figure out what my rate of change is if I just multiply some constant k times my population. So I could write it like this. I could write it like this, or I could write it like this, or finally, I can write it like this. And when that k is larger than 0, that's called the law of natural growth. And when it is smaller than 0, it's called the law of natural decay. And so when we have an equation like this, where the derivative, where we have some sort of derivative of an unknown quantity function. So we have this function y, it's an unknown quantity, and when we have its derivative, that's called a differential equation. Now when we think about trying to solve this differential equation, we're looking at a derivative that is some kind of constant multiple of itself, right? So we're looking for some type of equation that is a multiple of itself. Okay, and when you think about that, that's kind of has to do with exponentials. And so normally we have this exponential of y sub t equals ce raised to kt, right? This is an exponential that explains the rapid growth of something. Okay, and so when we look at maybe taking the derivative of this, if we use our differential rules, then we get this. And then we can go ahead and rewrite this as k times c e to the k r, k e raised to kt, which we know this right here is y sub t. So I could rewrite this as k times y sub t, which is our population at a given time. So it fits this equation right here. So it is a differential equation. So that means that the solving of this differential equation is always going to be in this form. To solve this differential equation, we just have to take k, some constant, times this c e raised to k t, in which that c times k is really just a number, right? Because this is just a number and this is just a number. So when I multiply them, it's just a number. So I'm just going to leave that as capital C. And when we plug in 0 in for this, for our time t, we just get 0, which is 1, which is just going to be c. So when we do c of c, or sorry, just c of our population at 0, our population at 0, sorry, is just going to be c. So when we write this thing, we can go ahead and solve any type of population by this theorem. So this theorem that gives us a solution to this exponential, or this differential equation, is just going to be in the form of this exponential function, because this is just c. When our population is 0, it's just c. So we have this theorem that allows us to solve this differential equation. And what we talk about when we talk about the relative growth rate, we're talking about how our rate of growth, that would be our derivative, dy over dt, divided by our population, population, which would just be y. Well, that's just equaling k, right? That's just dy over dt equals k times y. That's just divided by y. That's our k. So k is our relative growth rate. It's the rate of our growth over our population growth rate. So let's go ahead and look at a problem that asks us to find our relative growth rate. So here we have a problem. We use the fact that the world population was 2560 million, that's about 2.5 billion in 1950, and it was 3040 million in 1960, so that's like 3 billion. To model the population, so we want to use these two numbers to model the population of the world in the second half of the 20th century. We're going to assume that the relative growth rate is proportional to its size. That's the whole point of these differential equations. And we're going to look at find the relative growth rate, and then use the model to estimate what's happening in 1993 and what's happening today in 2020. Okay, so we can use a lot of this stuff with populations, whether population of bacteria, whether population of animals, anything like that where it's growing exponentially, right? Even you can look at viruses, see what's happening there. All right, so as we look at this, we want to measure the time in years. So we're going to let t equal 0. That would represent the year 1950. And then we want to measure the population. So we can go ahead and let the population just be P of t. It's a population with a certain time, at a certain time. We're going to let that be in the millions. Okay. And then, so that means that the population at time 0, which means in 1950, that is the 2560. And then the population 10 years from there, which is 1960, that would be 3040 million. Okay, and then since we're assuming that right here, it's proportional, that means our derivative, which we could say about p prime of t, the derivative is some kind of constant of our population, right? So we could write it like that, in which we saw from the theorem that we could use that in order to write this p sub 0 e k t, right? So we can use that theorem in order to write this. Okay, and then we can go ahead and enter in our population at year 0, which is 2560 EKT. And now we can find the population at any given time. Well, not quite any given time. First, we actually need to solve for k. So in order to do this, we need to plug in a t, right? Well, we do have a second t, it's 10. And we know p of 10. So we know p of 10 is the 3040 million. And we know the year of that is 10. So now I can solve this exponential, which we've been doing in this chapter and in pre-cal as well. So we're going to have to get the exponent, the base by itself, e. So then we have this fraction. I don't know it off the top of my head, but I can cancel those zeros if I wanted to, right? Because they both end in zeros. And then how do I get this down? How do I get rid of an exponential? Well, I take the log of both sides. And since I'm dealing with base e, I'm going to do the natural log of both sides. And so we can bring this out in front. And this is going to equal 1. So we just get 10k, 10 times k. We get the ln of 304 over 256. Oops, that looks sloppy. And then divide by 10. So I'm going to take the ln of this fraction and then divide that by 10. So I get this relative growth rate. Because remember from the last slide, our k was our relative growth rate. So we get this k as approximately 0.017185. Okay, to be more accurate, I could leave it like this. And that would give me a more accurate reading when I use this model. But we can go ahead and use this 0.017185. So then I write my model. So there's my relative growth rate. And I could write it as a percentage as well. I could do 1.7185% if I'm talking about percentage. Okay, now I can write my model, which is P 250 to 2560. Now I have my k 0.017185t. And now I can predict my population. Oh, sorry, population. So there's no apostrophe there. I'm just predicting my population. So come back here. Sorry about this. I don't want to redo this video. I've redone it plenty of times. So that's kind of how it goes for to find the population. So there's my model to find the population. Now I can predict what's going to happen in 1993, which is how many years after 1950? That's 43. So that'd be entering 43 in for my t, figuring out what this is. So that is population in 1993, which I can plug that in. I get 5360 million, which you could look up what the population was in 1993 and see if it's the same. And then we can do the year 2020, which is what, 40, 50, 70, which is today. So I type in 70. So 70 is going to go in for my t into this equation. And I get, which I think is actually pretty close. Maybe. Let me check real quick. And it is actually 7.6 billion. So we're kind of off of this a little bit, quite a bit, a billion or so away. So that's how you do exponential growth. I'll do another video. It's getting pretty long. So I'll do another video about exponential decay on the next one.